So this problem is pretty wordy, so I'll just simplify it. Essentially, we have some very large sphere which represents dark matter. And within that sphere, you have a ton of stars that are orbiting with respect to the center of that sphere. And the problem is asking us to look at the relationship between the star's orbital, radius r, and the velocity of the star. So some of the key things to keep in mind is that the problem gives us that the density of the dark matter is going to be constant, which will help us later. R1, which is the distance from the dark matter to the center, from dark matter center to a star in orbit, is going to be the more important radius, and I'll explain that in a second. And R2 is just that total radius of the massive dark matter sphere. So it's very notable that R1 is always going to be smaller than R2, making the velocity dependent in some way on the varying size of the cloud depending on the orbit of the star. So yeah, now we can continue and start solving for what that relationship is going to be. We are just going to use that expression we get from Kepler's law, which allows us to set the force of gravity equal to centripetal force, as the force of gravity is what causes that centripetal orbit. M2 and one of the r's will cancel, leaving us with just big G times M1, that M1 being the mass of the dark matter over r. And initially you might think that we just from this can already see the relationship between r and v squared, but the key thing about this problem is the fact that the mass of that dark matter is going to depend on R1. So since this is like a weird situation that I haven't personally seen as much, in which the smaller mass is literally inside the bigger mass, that's something we're going to have to account for. So the way I did that was just noting that the problem gives us that dark matter is spherical. So we already, just from memory, or you could look this up, you can note that the volume of a sphere is 4/3 pi r cubed. The problem also gives us that density is constant, keeping in mind that we're trying to change the equation in some way in relation to the mass. And so density is going to be useful since mass plays a role. So since density is mass times volume, and we're trying to potentially plug something in for m, which accounts for the r that's going to affect it, we can rearrange that density equation and plug in that volume of a sphere. You can see I did that, making m equal to the density times 4/3 pi r cubed. So yeah, once again, I just want to make this clear. The r, essentially the R1, that thing, that's going to become the sphere in this problem. So if the star was 10 million miles away, we would use that, and that would affect the volume of the dark matter and stuff like that. So it's weird, but that's the case for this. So we can plug in that expression we found for the mass, and into that equation we found with Kepler's law earlier. And once we do that, we essentially are just going to try to solve for velocity. And you can see that one of the r's will cancel, and since the v is squared and we're going to have to square root the other side, that because everything on the inside of the square root is multiplied, we can just yank out the r squared and it becomes r, which, because big G is constant, density is constant, 4/3 is constant, it allows us to see that the relationship between r and v is directly proportional. So radius goes up, the velocity goes up, and vice versa. So that's essentially the end of the problem. The really tricky thing here is just understanding the situation, because it's a weird one. Also, like, kind of suspending some of your belief, because this is a flawed model, because obviously certain things that we allow to be constant in this problem aren't going to be, or some things we made spherical that likely aren't spherical. For example, I doubt density is constant. The orbit of a star, I doubt it's circular, but in this case, the math turns out to be pretty simple. So yeah, that's the end of the problem. Thank you for listening.